In my last video, I talked about why the Commodore 64 and Commodore 1541 disk drive were so slow at loading programs. There's a lot of interesting history behind that, and once you understand the history, you can understand why there were so many fast loader solutions for the Commodore 64 and 1541. It's because it was pretty easy to make them faster. Now in that video, I did some benchmark tests to illustrate just how slow the 1541 was. And full disclosure, my benchmarking tests were awful. They were so bad, I had to do a follow-up video with better benchmarking tests. Now, this is the internet, and you can imagine in the comments section what it was like. A lot of people suggested, you guessed it, that I follow up with more benchmark tests. But what people really wanted to see were benchmark tests with fast loaders, various fast loaders. So instead of showing the stock drive times, how did fast loaders improve things for the C64 and the 1541? Now, I don't have a ton of fast loaders, but I do have a couple. So I figured I'd start with this one right here, the Epyx Fastload cartridge. Now, I thought I'll start my video with a little blurb about how this thing works before I just jump right into benchmarking. And I assumed this thing came out in 1984. I just thought the internet would be loaded with descriptions and all kind of reverse engineering of exactly how this cartridge works. To my surprise, I found nothing on the internet about how this works. So I know you asked for benchmarking, but I'm going to start with a healthy dose of here's how this thing works, and then maybe I'll do some benchmarking at the end. So let's get started. Before I dive into how Fastload works, I'll start by explaining how loading a program works using a stock Commodore 64 and 1541 disk drive without a fast loader. It's obvious that a wire is connected between the Commodore 64 serial connector and the serial connector on the 1541 disk drive. Programs are transferred from the 1541 to the C64 over this wire using what are called TTL signals, or transistor-to-transistor logic signals. When the voltage on a wire is near 5 volts, it's a logical 1 bit. When it's near 0 volts, it's a logical 0 bit. You can see that this connector has 6 pins, so there are 6 individual wires between the C64 and the 1541 disk drive. The pins are 1. Service request, 2. Ground, 3. Attention, 4. Clock, 5. Data, and 6. Reset. So how are these wires used to transmit data? Service request isn't used at all, and ground is just a ground. Neither of those are used to transmit data. Reset and attention are both used as control lines, not for data transmission. So out of the 6 total wires, it's just the clock and data line that are responsible for transmitting data between the C64 and the 1541. Knowing this, if I want to show you how a stock C64 and 1541 transmit data across these lines, I can connect a logic analyzer to the lines and watch the ones and zeros, or highs and lows, travel across the lines. I'm using a Salia Logic Pro 16 here, and I connected to points on the 1541. For this entire video, I'll be showing examples of loading this one-line Hello World basic program from disk. This is the Salia Logic user interface. I connected probes to attention, clock, data, and reset, and I labeled them over here on the left. H indicates where the signal on a wire is high or near 5 volts. L indicates when the signal on the wire is low or near 0 volts. What you see here is every signal that crosses the wires from the moment I enter load quote hello quote comma 8 on the Commodore 64 until the 1541 has completed transmitting the program to the Commodore 64. I'll zoom in to show you more detail. The wire protocol starts with the C64 pulling the attention line low. This tells every device on the bus to pay attention. The 1541 responds by pulling the data line low. The C64 then pulls the clock line low and holds it low until it's ready to send some data. I'll zoom back out here so we can move on. The C64 releases the clock line high when it's ready to send a byte. The 1541 releases the data line high to acknowledge that it's ready to receive a byte. Finally, the C64 pulls the clock line low again to signal that it's going to begin sending the data byte. You'll always see 9 clock pulses per byte when data is traversing the bus. The first is the handshake I just described, and the remaining 8 are the clock pulses that correspond with data bits. Data is sent 1 bit at a time on the data line, with the least significant bit of the byte being sent first. The signal on the data line is valid with the rising edge of the clock signal. So here, where the clock signal is rising, the data line is low, so that's a logical 0. These next 2 bits are also 0. Then the data line is high where the clock signal is rising, so this represents a logical 1. Continuing on, we have a 0, a 1, a 0, and another 0. Converted to hex, the 8-bit binary value 00101000 is 28. Because the attention line is pulled low, devices on the bus will treat this as a command byte rather than a data byte. 20 is the Commodore DOS bus control code for the listen command, and the 8 indicates the device number. So this command tells device 8 on the bus to listen. It's the C64 selecting device 8 on the bus. The next byte is F0, and the attention line is still pulled low, so this is another bus control code. F0 tells the 1541 to open channel 0. The C64 releases the attention line high now, so the 1541 will treat these next bytes as data instead of commands. The first byte of data is hex 48, which is PETSCII character H. Notice the longer acknowledgement sequence here. This is what's called an EOI condition in Commodore's bus protocol. Now, I won't cover the specifics in this video, but this signals to the receiver that the next byte will be the last data byte. The last data byte is PETSCII character O, so these 5 data bytes the C64 sent to the 1541 are telling it the name of the file we want to open. And here the C64 pulls the attention line low again, so the next byte will be a bus control code. That bus control code is a 3F, which means unlisten. Zooming back out and looking over here, this is the 1541 sending the file data, which is a Hello World basic program, back to the C64. Now, for the sake of brevity, I didn't cover every detail in that first part of the wire protocol, and I'm going to leave out even more detail here. It's only important to know that data is sent from the 1541 to the C64 using that same wire protocol I already showed you. The difference is the 1541 becomes the sender and the C64 is the receiver. While I still have the logic analyzer open, I'll take a moment to measure how long it takes each of these 3 bytes to send. This one right around 2 milliseconds. Also around 2 milliseconds for that byte. And same, delta t is about 2 milliseconds for each byte to be sent. At 2 milliseconds per byte, the data transfer rate for a stock C64 and 1541 disk drive would be about 500 bytes per second. That doesn't account for things like drive seek time, so the actual average will be slower. We're making pretty good progress here. We now have a really good understanding of exactly how the stock serial protocol worked between a Commodore 64 and a 1541. Now that we know that, what could be done to make it faster? Well, back in the day, there were a ton of different fast loader solutions, and they were all over the map in how they worked. 1541 flash that I showed in my last video, that required hardware modifications. New kernel ROM in the C64, new drive ROM in the 1541, 2 additional wires in between them. What was the other one? Dolphin DOS back then. That gave you full parallel data transfer. I mean, obviously it required a parallel cable, but insanely fast back in the day. Most of them, however, weren't that complex. What most of them did was just rely on the fact that that native protocol on the wire that we just looked at, it wasn't very fast. It was meant to be reliable, so it was pretty easy to come up with ways to make that transfer faster. That's what most of them did, and that's how Epyx Fastload works too. So, now that we know that, let's go take a look at exactly what Epyx Fastload did. Epyx Fastload comes on a standard Commodore 64 cartridge. You just plug it in and it's ready to go. When you load a program, it'll speed it up for you. How does that happen? You don't need to type a different command, so how does Epyx Fastload change how the Commodore 64 load command works? When you type the Commodore basic v2 load command, that internally calls the C64 kernel load routine. If you look at page 286 of the programmer's reference guide, you'll see the call address for the kernel load command is FFD5. I'll use a machine language monitor to look at what's at FFD5.
I'm using Hessmon, but you can use any one you like. When you disassemble the code at FFD5, you'll see that it jumps to F49E. I'll disassemble F49E now, and I need to get a little bit of extra code, not just one instruction. 3 instructions down, there's a jump instruction, and parentheses indicate that it's an indirect jump, so it won't jump to address 0330, it will jump to whatever address is stored at 0330 and 0331. That address is F4A5, so the actual kernel load routine executes from F4A5. 0330 and 0331 are in RAM, so any program is free to modify the address stored there and cause the kernel load routine to execute from some other location. This is what Epyx Fastload does in its initialization routines. To show you that, I'll use the machine language monitor that's built into Epyx Fastload to look at memory location 0330 and 0331 while Epyx Fastload is running. There you go. When you run a load command from BASIC with Epyx Fastload installed, the kernel load routine executes from Fastload cartridge ROM at DF2E instead of C64 kernel ROM at F4A5.
We know what causes the Epyx Fastload cartridge code to run instead of the C64 kernel code when you type a load command now. Next, we need to understand exactly what it is that the Epyx Fastload load routine does. To be able to explain this to you, I had to learn how it works myself because, as I said, I didn't find it documented anywhere. What I did was, I did a complete disassembly of the entire Epyx Fastload load routine. I'm not going to go through it line by line in this video because I think that would make for a long and boring video. But if you're interested in the code, I'll throw a link in the description of the video. In this video, we're just going to cover the high points of how it works.
I'll walk you through the Fastload wire protocol using a logic analyzer in the same manner as I did for a stock C64 and 1541, so I wanted to show you the full protocol of both in one view so you can get an appreciation for just how differently Fastload does things. These aren't quite exactly to scale, but I'll give you a little spoiler up front and tell you that for loading a one-line Hello World basic program, Epyx Fastload is slower than a stock C64 and 1541. By the time I'm done, you'll understand why. Let's get started with walking through the logic analyzer output, loading the same one-line Hello World basic program using Epyx Fastload. The logic analyzer probes were connected to the same points on the 1541, so the only thing that's different here is the use of the Epyx Fastload cartridge. What you're seeing here is everything that crosses the wire from the moment I entered load, quote, hello, quote, comma, 8 on the C64 until the 1541 completed transferring the file to the C64. I'll zoom in to get started. The first point I need to make here is that, as of now, even though we're using Epyx Fastload, all the wire protocol you see here is still standard Commodore serial bus protocol. Keep in mind that Commodore's bus was designed to be shared by multiple devices, so there could be a printer, a 1541 disk drive, and who knows what else connected to the bus. The 1541's running its stock drive ROM code, so at this point, Fastload needs to abide by all the standard Commodore bus protocol semantics. I'm going to skip most of those protocol semantics and just focus on the bytes being sent from now on. And the first byte we see on the wire here is hex 28. The attention line is low, so this is a bus command which is telling device 8 to listen. This byte is hex 6F. The attention line is still being held low, so this is another bus command, which tells the 1541 to open channel F, which is 15 in decimal. I'll turn to page 15 of my VIC 1541 user's manual here, and that tells us that channel 15 is the command channel. Indeed, if you've ever formatted a floppy disk, you've noticed that you use channel 15 for that. So whatever comes next is going to be a DOS command that will be sent to the 1541. The attention line is high now, so this is data. The byte is hex 4D, which is Petsky character M. The DOS command Epyx Fastload sent to the 1541 is M-W. I'll refer back to the VIC 1541 user's manual so we can see what that does. MW is the memory write DOS command. It allows you to write up to 34 bytes at a time into drive RAM. The format shows that it takes 3 bytes worth of arguments. First, a 16-bit start address. That specifies the address we want to write to in RAM. Then it takes a single byte that specifies how many characters we're writing. Let's take a look at the next 3 bytes that Epyx Fastload sends to see what they are. Hex 19 is decimal 25, so Fastload will upload 25 bytes to the 1541 drive's RAM starting at hex 0180. I put together a memory map of the 1541 to show where that is, and it's on the stack. However, apparently this section of the stack isn't actually used. I'm going to zoom out for a moment here and save us some time. The section up here on the left is the MW command we just looked at. We only examined 8 bytes of that in detail. The remaining bytes in this chunk are the 25 bytes of data that are uploaded to RAM from hex 0180 to 0198. There's no value in looking at every byte. The next 2 chunks of protocol to the right are also memory write commands, and they write 25 bytes each to the 1541's RAM for a total of 75 bytes. I'm going to skip over those. The protocol's the same for all 3 of the memory write commands, only the data is different. So let's move on to this next chunk over here on the right. The attention line is high here, so whatever it does send, it's going to be treated as data, not a command byte, and it is Petsky letter M. Epyx Fastload sent an ME DOS command. You can probably guess what this does, but I'll show you in the VIC 1541 user's manual. ME is memory execute. The 75 bytes that were just uploaded to the 1541's RAM were 6502 machine code. Remember, the 1541 is a full-fledged computer in and of itself. It has a 6502 CPU, RAM, ROM, and I/O chips. The 1541 has been happily running the Commodore DOS code up until this point, but once this ME command is sent, it will begin to execute the code that Fastload just uploaded to it. The next 3 bytes are part of the ME command. 2 bytes are the execution address, and then a carriage return to end the command. That was the carriage return, so the execution address is hex 01A9. As of this moment, the 1541 is now executing code that was uploaded to it by Fastload instead of executing the stock Commodore DOS ROM code. At this point, the 1541 is running Fastload code and the C64 is running Fastload code, so you might think it's the Wild West now and that Fastload can do whatever it wants. It can to an extent, but as I mentioned before, it's a shared bus. There might be another disk drive or a printer connected to the bus, so Fastload still has to adhere to the Commodore serial bus semantics at least to the extent that it doesn't confuse other devices on the bus. With the attention line pulled low, this byte is a CBM bus control code and 3F is the unlisten bus control command. This is really for the benefit of other devices. I'll zoom out again now. What you're looking at here is a really cool optimization. The full Fastload drive code requires another 256 bytes of code to be uploaded to the drive, and the stock Commodore bus protocol wasn't fast. So rather than use the stock Commodore bus protocol to upload all the necessary code, the first 75 bytes of code that were uploaded using MW commands implement a slightly faster wire protocol. It's not the Fastload wire protocol that will be used to stream file data from the 1541 to the C64. That's even faster. This is what they were able to implement in a mere 75 bytes of code. The really fast Fastload protocol is implemented in the next 256 bytes that are sent to the drive, and that's what you see here. It's another 256 bytes of code being sent over the wire from the C64 to the 1541. The code that's currently executing on the 1541 was uploaded to hex 0180. The additional 256 bytes of code will be uploaded to data buffer 2 at hex 0500. Now I can zoom back in and show you how this semi-fast interim Fastload wire protocol works. It starts with the 1541 pulling the clock line low. Then, the 1541 waits for the C64 to pull the data line low. Once the C64 pulls the data line low, the 1541 releases the clock line high. Then, the 1541 waits for the C64 to pull clock low. When the C64 does this, this is where data transmission begins. Like the stock Commodore bus protocol, this interim Fastload bus protocol is sending one data bit at a time on the data line. The least significant bit is sent first. Data is valid on the data line with each clock transition, so the 4 even bits are sent when the clock is low, and the 4 odd bits are sent when the clock is high. When the data line is low, it's a logical 1. When the data line is high, it's a logical 0. This first byte is 001000000 or hex 20. After the 1541 stores that byte in its RAM, it goes back into a wait loop, waiting for the C64 to pull the clock line low again, then it reads another 8 bits. It does this until all 256 bytes of additional fastload code have been read and stored in RAM. So while there isn't a two-way handshake like the Commodore bus protocol does, the wait loop at the first bit of each byte acts to synchronize the protocol. Now, while I'm here, I'm going to do some measurements. That way we can see how this protocol compares with Commodore's standard bus protocol timing-wise. So this first byte measures out to be 320 microseconds. And this one, 321 microseconds. Finally, we'll measure 3 bytes, just like we did on the Commodore bus protocol. And for this one, 277 microseconds. So if we're looking at about 300 microseconds to send a byte of data, that works out to be about 3,300 bytes per second for Epyx Fastload uploading to the 1541 compared to 500 bytes per second for Commodore's standard serial bus protocol. There's one more thing to show you here in this section of the wire protocol. After the C64 uploads the final 256 bytes of code to the 1541, it sends the last bit of data the 1541 will need to be able to load a file, the name of the file. This first byte is a 5, which tells the 1541 the length of the file name. Then the C64 sends the file name in reverse byte order. There you have it. Hello. Is it me you're looking for? Let's zoom back out here, and to describe what happens next, I need to step away from bus protocol for a moment and talk about the DOS code that runs on a stock Commodore 1541 disk drive. Commodore's DOS code has 2 main functions that are shown here. The IP, or interface processor mode idle loop on the left, that's the main thread of execution on the 1541. It handles all the communication on the serial bus with the Commodore 64. The FDC, or floppy disk controller routine shown on the right, executes every 10 milliseconds via an interrupt fired by one of the 6522 VIA chips in the 1541. This is the code that handles actual disk I/O. Now that Fastload uploaded its own drive code and began executing it, the IP routines on the left are no longer running. However, the FDC routine on the right is still being executed as an IRQ handler each time an IRQ fires. So the Fastload code is responsible for doing the necessary setup, placing a command in the job queue, and calling the parseXQ routine itself. I'll get back to wire protocol now. I already covered this whole bit over here. That's Fastload uploading code and the file name to the 1541. Over here is where the Fastload code running on the 1541 disk drive begins to send data back to the C64. So I'll zoom in on a bit of wire protocol here and explain how it works. Fastload uses the clock and data lines to send data, so it's sending 2 bits in parallel. When a line is high, that represents a 0. When it's low, that represents a 1. The Fastload code on the 1541 is the sender, so it's controlling both the clock and data lines for each data byte sent. Bits 5 and 7 of a byte are sent first, with bit 5 on the data line and bit 7 on the clock line. So here, bits 5 and 7 are both 0. Bits 4 and 6 are sent next, so another 0 and 0 bit. Bits 1 and 3 are both also 0. Bit 0 is a 1, and bit 2 is a 0. The first byte sent is hex 1. This transfer is done using CPU cycle exact code. Again, there isn't a mutual handshake in the protocol like the stock Commodore bus protocol uses. Rather, the C64 holds the data line low after each byte and releases it when it's ready to receive the next byte. I'll show you a few more examples. I just got done saying this is CPU cycle exact code, so why is the C64 holding the data line low here longer than it was for previous bytes? The VIC-2 chip in the C64 borrows about 40 CPU cycles from the 6510 when it draws the first pixel line of each text row. If that were to happen while the 1541 was sending a byte, the C64 would miss data. So the fastload code on the C64 watches the raster line and holds the data line low to avoid bad lines. Again, I'll take some measurements while I'm here. "90 microseconds. "111 microseconds. "108 microseconds. And this longer one is 197 microseconds. That averages out to about 126 microseconds per byte. That's a transfer rate of nearly 8,000 bytes per second with Epyx Fastload compared to 500 bytes per second on a stock C64 and 1541. Of course, this does not take drive seek time into account, nor does it account for the time it takes to upload the Fastload code to the 1541 before loading can begin. So the actual transfer rates are going to be quite a bit slower than this. So how can Epyx Fastload be so much faster, and why didn't Commodore just do the same thing? The Epyx Fastload code is specifically written to work between a Commodore 64 and a 1541 disk drive. Every detail of the sending and receiving hardware is known and fixed. So if you look at this code, it's transmitting as fast as the CPU on each side can send and receive data, right down to the CPU cycle. There are no ops in place on the C64 sending side to allow the 1541 enough CPU cycles to read the bus signals, perform bitwise manipulation to convert to byte data, and store in RAM. Commodore engineers didn't have that luxury. They were designing a general-purpose serial bus protocol that needed to work with any device that was connected to it, so they couldn't make any guesses about the system clock speed of any sending or receiving devices on the bus. They also had very little time available to them. I went into more detail about this in my previous video. Given what they were up against, they designed a reasonably reliable and generic protocol that would support any device, but it just wasn't fast. I mentioned earlier in the video that Epyx Fastload was slower to load my Hello World basic program than a stock C64 and 1541. In case it's not obvious, that's because before Fastload even begins loading a program, it has to upload 331 bytes of data to the disk drive. You can see on the left side here how much time that takes compared to a stock C64 sending a load command. However, once the data starts sending from the 1541, Fastload sends much faster, just not fast enough to offset that initial upload time for my example Hello World program, which is only 17 bytes of tokenized BASIC. For sufficiently small enough programs, Fastload will be slower than a stock C64 and 1541.
Video that required a new kernel mod. We're making good progress here. We now have a pretty good understanding of how fast loaders. We're making good progress. Now we know why the Epyx Fastload cartridge code runs instead of the C64 kernel code when you execute a load command. Now we understand how the Epyx Fastload code runs instead of the C64 kernel code when you type a load command. Next, we know how the Epyx Fastload cartridge code runs now instead of the C64 kernel code when you type a load command. The next thing I want to talk about is exactly what the Epyx Fastload load code does. Now, for me to be able to